Hello there. My name is Eduardo Benavides, and this is my presentation for my final project in CSE 545. And it is about solving the windy postman problem, also known as the WPP. So let's get started. So this presentation is essentially divided into three parts. What is it? What is the WPP? How I solved it? And what were my results? So what is a WPP? Well, a WPP is a variant of a CPP, and a CPP is the Chinese postman problem. Now, looking at the little example I have to the left here, the Chinese postman problem, it either has undirected or directed edges in the graph, and each edge has a single weight. For the solution, you must find a minimum path where you traverse each edge at least one time, and you must traverse along the least pairings of odd vertices, which creates arcs. And you must return to your origin point. So look at this graph. Let's say you start at node A. You must traverse all of these edges at least one time and end back at A. Now you can see these arcs being created. These arcs get created because looking at this graph, you'll notice that there's two nodes that have an odd degree, node A and node H. Because they have an odd degree, you're going to be creating this arc that connects them directly. Obviously, there are multiple ways they can be connected directly. Starting at node A, you go to B, E, F, H, or A, B, D, F, H, or A, C, H. But you want to find the minimum path, making the minimum arc. In this case, going from node A to B to F to H creates that arc that must be traversed. That's CPP in a nutshell. So what makes the windy postman problem, the WPP, different is that it has undirected edges, no directed edges at all. And each edge has two weights. Those weights represent the direction the edge is being traversed in. So looking at this graph right here, for node 1, right? You want to go from node 1 to node 5, it might take 12 units. We'll use minutes. So it might take 12 minutes, right? But from node 5 to node 1, same edge, same path, might take 14 minutes. I say might, it will, based off this. So that's what it is. That's the windy postman. You can travel one edge one way, have this weight for it, but if you travel that same edge back, you're going to have a completely different weight. The solution is pretty similar. Create the minimum solution where each edge is traversed at least one time. You have no arcs to worry about, but you also want to end up where you started. So if you started at node 1, you want to traverse all of these edges at least one time and then back at node 1. So that's a WPP. Now in 1979, I hope I'm pronouncing his name right. Um, Edward Manika, I apologize, but he actually did a research paper about the Chinese postman problem and for mixed networks. And in doing so, he referenced or discussed the windy postman problem. And in there, he was able to reduce it to a mixed Chinese postman problem. And MCPP is just a CPP, but with undirected and directed edges. But he was able to reduce a WPP to that mixed CPP. Apologies. And because in his paper, that mixed CPP is NP complete, that meant the WPP is also NP complete. And because of that, and because of it being very interesting, that's why I chose to do a WPP for my project. So how did I solve this? Well, I used a genetic algorithm, wisdom of crowd hybrid. to solve it. I did it in Python, and pretty much a genetic algorithm simple in the case where it's a search algorithm where it has this idea of natural selection to create the optimal solution. So kind of going through this little snippet of the algorithm I created. Um, for an X number of generations, we'll say 10,000. It will go through this population size. We'll say 100. It's 100 population size, meaning there are 100 different individuals. The individuals are tours in this case. And for each generation, it's going to find the most optimal tour. After it does that, it selects the parents, selects a couple parents, and with those parents, it creates children, and that creates this new population, this new generation. And it does that for 10,000 generations. And it does this in the hopes of finding the most optimal solution. Where WOC comes into play is for, at least for my algorithm, for about every 100 generations, these steps are going to be in place to where it selects an X number of experts, and within those experts, it concludes its own individual solution, and that solution is superior to the other individuals, and it is placed at the end of the new population that was created by the genetic algorithm. And so that population with that expert solution is put into finding the optimal solution. That's pretty much the algorithm in a nutshell in layman's term. Now, testing data. The testing data resembles what a TSP file would look like. That's because I created this myself with TSP files as an inspiration. Not that hard to do. All I did was add a couple things like the edge weight section, but the no coordinate section is pretty similar. The main difference is that we're not using float values, we're using integer values. And these are random coordinates between 1 and 100, the random XY coordinates. The edge weight section, though, is the important one. So to discuss what it is, the first number is the starting node. The last number is the end node. The second number is the end node. The third number is the weight from the starting node to end node. And the last number is the weight from the end node to starting node. So that's how you kind of read this. We have 6 testing files to look at. So I want to try to get them all to you in the next 7 minutes. So let's go on to the results. So we start with random 4 and random 4 part 2. So going back a little bit, you'll notice this is random 4 and this is random 4 part 2. I wonder if I can highlight it. No, not right now. Not right now. You'll notice that they have the same number of nodes and they're the exact same coordinates, so same positions. Part 2, though, has 2 more edges. Now, you could solve this with brute force. 4 nodes, I could probably, I'm not saying I could, I did find the minimum solution with brute force. It's not that many nodes, not that many edges to go through. Pretty simple. So obviously the algorithm was going to find the solution pretty consistently. And that was what I was looking for when I was doing these testing in the first place. I was trying to find if it can find the solutions consistently. But mainly for these 2 files, I wanted to see the effect the number of edges has on the algorithm. And obviously, the prediction was it was going to take longer, and this just backed that prediction. This is the generation plots for the random 4 file. Random 4 part 2 follows the similar pattern. It's almost identical. I think for run 11, it had a little problem, but other than that, it doesn't struggle really. And for both of them, consistent answers is just for part two, which is this one above, it takes a little bit longer. That's all. So that means the number of edges, more number of edges you have, the longer this will take. Random 5 and random 6 looks at the number of nodes. They have the same number of edges. Random 6 obviously has one more node. But that one more node adds a lot more time in comparison. All right, for the number of edges, I believe it only added like 20 seconds, I believe. Total. For this one, added 30 seconds for adding one more node. So obviously the time is a big difference between number of nodes and edges. So whether adding more nodes or more edges, it's going to be longer to do. The big thing to look at though is these generation plots. Now, they didn't struggle at all, but the random 6 one didn't struggle really at all because at run 11, it found a solution and it stuck with the solution all the way through, which tells me when I was creating this presentation, because I didn't notice it during the initial testing, it tells me that the relationship between the number of nodes and the number of edges is vital when solving this problem with this algorithm. Consistent answers all around, nothing changed, all right? They got the minimum solution for their respective files. But for random 6, at one run, it was just very easy for it to find that solution. Even though it had one more node, took longer, found that solution immediately. So I look at random 8, and this shows our first signs of struggling. Because if you look at the generation plot, struggles a little bit. For like 3 of the runs, it took to at least 6,000 generations for it to find an answer. But also, in one run, it found the wrong answer, you could say, because it found a distance of 78 when all the other runs found the distance of 77. So this shows our first piece of inconsistency. Now to battle that, you just need to adjust the parameters. I'm sure if I adjust the parameters in the algorithm to do maybe 5,000 more generations, maybe 50 more in the population, we will get 77 all the way around. But the fact that it got a different answer is huge. Now, 8 nodes, 13 edges. This is the best path. 8 nodes, 13 edges. I say that because random 10. 10 nodes, 12 edges, easier time at finding the solution based off the generation plots, easier time. Some of these runs look like a run 4, run 5 plot, and each run found the proper answer. Now, it took forever, 30 minutes per run. That's 30 minutes in seconds. That's 7 hours in minutes, right? So 30 minutes per run, but it found the answer. Did not have any inconsistencies with finding the answers, and it had an easier time doing it, even though it had 2 more nodes. But because it had 2 more nodes, but 1 less edge, easier time. So I think towards the end of the testing, that was showing me that there was a relation, but I really didn't put it together until the last minute, sadly. But it helped me with coming up with a conclusion based off these observations, because the takeaways from it is that the genetic algorithm with the wisdom of crowd steps is great to generate consistent solutions. Depending on the number of edges and nodes, you might have to adjust the parameters a little bit, but other than that, you're getting consistent solutions all around the board. So it's really good for that. And initially, when I was testing, that's what I was looking for. Could it be consistent? And it was. I wish I would have tested larger data sets to see if it keeps up with that consistency and backs up the claim of needing to adjust the parameters for larger data sets. That should have been something I should have tested, and I didn't, so I do regret that. But the big regret is the fact that I didn't catch the relationship between the number of nodes and edges before until literally making this presentation. because then what I would have had a more focus on was creating data files that had that focus of that relationship, that ratio. Because I would have loved to seen how much the algorithm would have struggled or how easy of a time it had when that ratio was adjusted. So that's something that I would like to see in the future. But overall, if you're okay with how long it takes, the genetic algorithm with WOC steps works perfect for this. For the WPP problem, not the quickest in the world, but works pretty well for it. Gets you the solution, just might take some time. But yeah, that's all for my presentation. And yeah, thank you very much. I hope you have a good day.